Tonight's lecture is called Changing Clouds in a Changing Climate and is presented by Dr. Joel Norris of the Scripps Institution of Oceanography. Dr. Norris's research is centered on investigating the role of cloudiness in the climate system and causes of coupled atmosphere-ocean variability. As Dr. Norris explains, this involves understanding interactions to both the largest, smallest, and the in-between scales. To make progress on this problem, it will be necessary to integrate results obtained from different observational techniques and modeling from large eddy simulation to global climate models. Dr. Norris received his Bachelor of Science in Geophysics from the California Institute of Technology in Pasadena and his PhD in Atmospheric Sciences from the University of Washington in Seattle. His long resume includes work with the Jet Propulsion Laboratory in Pasadena, the National Center for Atmospheric Research in Boulder, Colorado, and the Geophysical Fluid Dynamics Laboratory in Princeton, New Jersey, before joining Scripps in the fall of 2000. I want to thank Dr. Norris for taking time out of his busy schedule this evening to join us. We are honored to have him here as our guest and the Birch Aquarium at Scripps for this evening's Perspective Lecture Series. Ladies and gentlemen, please join me in welcoming Dr. Joel Norris.
Thank you. It's a pleasure to be here. Instead of giving a comprehensive description of all the research I've done, I thought I'd give more motivation for why I think this is a very important topic that I've been working on, the relationship between clouds and climate system, especially in a changing climate from anthropogenic global warming. Here's just a brief outline. I'll start off by talking about the effects of clouds on the Earth's incoming solar radiation and outgoing thermal radiation, how these effects can act as cloud feedbacks on global warming and climate change, looking at cloud feedbacks and global models, asking the question, can we trust them? Look at observed cloud trends, are they real or are they not? And end with a summary. So I'll begin with just everyday effects of clouds, just what we experience in our regular lives. Cloudy days are relatively cold. This is because clouds reflect solar radiation back to space, and of course clouds with greater thickness reflect more solar radiation. It's also the case that cloudy nights are relatively warm. This is because clouds emit more thermal radiation down to the surface than does a clear atmosphere, and also warm clouds emit more thermal radiation than cold clouds. Now this effect on thermal radiation also operates just not at the surface but also at the top of the atmosphere. And it, in fact, has a greenhouse effect rather similar to the, say, greenhouse effect from carbon dioxide and water vapor. Clouds are higher in the atmosphere and they're colder than the surface just because temperature decreases as you go up. And that means clouds emit less thermal radiation to space than does the unobscured surface if there were no clouds present. And higher clouds are colder and emit less radiation than lower clouds. And thus clouds act as a blanket to keep the Earth warmer. In fact, you could call clouds a reflective blanket because they both reflect solar radiation and also absorb and emit thermal radiation. So for example, with a low-level cloud here, rather low in the atmosphere, like stratocumulus, these low-level overcast clouds we often get around San Diego, they have a strong reflection of solar radiation back to space. But their greenhouse effect is rather weak because whatever thermal radiation that's emitted by the Earth, it gets absorbed by the cloud, but because the cloud, since it's low, is almost as warm as the Earth is, it emits almost the same thermal radiation to space. So here we just have the reflection of solar radiation back to space, so overall, these types of clouds act to cool the Earth. On the other hand, high-level clouds, they're often very thin, and so they let solar radiation come through, penetrate, get absorbed at the surface. But on the other hand, since they're high, they're rather cold and emit very little radiation to space relative to what the surface gets. So they absorb this radiation coming up from the surface and only emit a little bit farther up to space. So overall, they're warming the surface by reducing the amount of thermal radiation that can escape and act, that would be cooling the Earth. And so sometimes there are thick clouds also that both reflect solar radiation back to space but also reduce the amount of thermal radiation going out to space. And these can have a near zero effect. Just some examples of low-level clouds. We have cumulus here, these rather small puffy clouds. They have a weak greenhouse because they're not very high above the surface of the Earth. But they do reflect sunlight back to space, but overall not very much because there's a lot of clear areas between them. They don't have very much sky cover. On the other hand, stratocumulus is much more widespread. There are many fewer breaks in stratocumulus, and so they have a strong reflection of sunlight back to space, but only a weak greenhouse effect. So they act to cool the Earth. As an example, some high-level clouds, like cirrostratus here, you see the blue sky behind it, and that shows that these clouds are pretty thin, and a lot of the sunlight that would come through isn't reflected, but actually penetrates through to the Earth. But on the other hand, they're rather high up and have a rather substantial greenhouse effect in restricting how much thermal radiation can escape to space. So they end up having a moderate warming effect compared to if they weren't present. Cirrus are similar, although they're not as much sky cover as like the cirrostratus here. Examples of thick clouds, one of them here is cumulonimbus, which is like a thunderstorm cloud. When you're underneath them, they have large sky cover, they're very thick, it's very dark underneath them, so there's strong reflection, but also because they're so tall and their tops are very high in the atmosphere, they also have a strong greenhouse effect. Another thick cloud is nimbostratus that we get when it rains substantially here. And again, you see how dark it is underneath, so there's a lot of the solar radiation is being reflected back to space rather than penetrating to the surface. They also have a rather strong greenhouse effect, and these cancel out. The cooling and a warming effect come to near zero. Here is a map of the annual mean cloud reflection around the world. This was obtained by satellites, and this is just the reflection that comes from clouds. It doesn't include reflection that would come from ice and snow or bright land surfaces like deserts, just the clouds. And you see clouds are reflecting solar radiation. So in some places very little is reflected, these greens, but in other places like these grays there's a substantial amount of solar radiation reflected by clouds. And I'm not showing data for the polar regions because it's rather difficult to figure out what the clouds are reflecting when you have a cloud over a bright snow surface. They're both very bright and highly reflective, and it's hard to detect clouds there. Okay, so some of the clouds I've talked about before, the cumulonimbus, these tropical thunderstorm clouds. They're prevalent, like say here in the rainforest over equatorial Africa, South America with the Amazon here, many of those. They reflect a lot of solar radiation. Also over Indonesia here, a lot of precipitation, thunderstorms, highly reflective clouds. And here along what's called the intertropical convergence zone, where you have flow from the southern and northern hemispheres converging and producing rain and deep convective clouds. At the higher latitudes, we have nimbostratus associated with frontal systems that go along the mid-latitude storm tracks across the North Pacific, the North Atlantic, and also the Southern Ocean. Here are regions of where stratocumulus is present. These are the low-level clouds, overcast clouds that often occur in San Diego. We see there's a big region of them off the coast of San Diego here. There's also, here off the coast of Peru and Namibia, these stratocumulus clouds are preferentially formed in eastern subtropical oceans, but they also occur at mid-latitude oceans associated with storm systems. And finally, we see some clear regions here, like for example, these regions over deserts have very few low clouds at all because it's very dry at the surface, so there's very little reflection by clouds. And also over the ocean, there are small cumulus clouds here because there is a source of moisture there, but they're very small and they don't do much reflection in these subtropical oceans here, 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 and there. Here is a map of the annual mean cloud greenhouse effect. This shows how much radiation is prevented by clouds from getting out to space. So these numbers are negative. This is how much the outgoing radiation is reduced by the cloud greenhouse effect. And because the outgoing radiation is reduced, it's retained by the Earth system and acts to warm the planet, unlike the reflection, which acts to cool. So big regions of the reduction in outgoing radiation occur in where we have these tropical thunderstorm cumulonimbus clouds in the rainforests and the warm pool here in the intertropical convergence zone. There's also a lot of cirrostratus, that's outflow from the anvils of these cumulonimbus. So they have a strong greenhouse effect. There's also a greenhouse effect from the nimbostratus in the mid-latitude storm tracts. But then you see several of these regions here over the deserts and over subtropical oceans where it's mainly clear sky above the surface, above the low-level cumulus clouds, and there's just a little bit of cirrus, so the reduction in outgoing radiation is very small in these regions. So here on the left I have the mean cloud reflection, the mean cloud greenhouse effect. If you combine them, you get the net effect, which is below, and we see that over most of the globe we have these blues, which means, or greens. So that means in the net effect is the solar reflection wins out over the greenhouse effect, especially where the stratocumulus regions are off of California and also in the mid-latitudes. There's only a few places like over the Sahara Desert where clouds have a net warming effect because there's just the high-level cirrus there. Now, if we average over the entire globe, just to get a single number for the average reflection of solar radiation by all clouds, that's 48 watts per square meter. There's probably some more recent results would update this a bit, but not by very much. The reduction in outgoing thermal radiation by all clouds is 31 watts per square meter, and the net effect is 17 watts per square meter. And so we can see that clouds in aggregate act to cool the Earth in the current climate state. And it's important to realize that this is in aggregate because any particular cloud may have a warming effect, or certain parts of the world, the clouds may have a warming effect. Now, to make a comparison of how strong this is, we can look at how much the increase in carbon dioxide since pre-industrial times has affected the radiation budget. So since about 1750, before fossil fuel were burned, carbon dioxide has risen in the atmosphere from about 280 parts per million to 380 parts per million, which is about a 35% relative increase in carbon dioxide concentration. This has reduced the outgoing thermal radiation by about 1.6 watts per square meter as compared to pre-industrial times. And just to get a sense for what this is like, this reduction in outgoing thermal radiation means the Earth is getting warmed up by this much. And so it'd be equivalent to putting 60-watt light bulbs every 6 meters over the entire Earth, the warming that a 60-watt light bulb would produce. Now, if we compare the cloud effect with the CO2 effect, so carbon dioxide about 1.6 watts per square meter since pre-industrial times, about 35% relative increase in carbon dioxide. Well, that's equivalent to just a 3% change in reflection of solar radiation by clouds, a 5% change in the reduction of outgoing thermal radiation by clouds, or a 9% change in the net effect of clouds on the Earth's radiation budget. And so we can see that Earth's radiation budget and consequently its temperature are very sensitive to small changes in clouds, much more sensitive to changes in clouds than they are to carbon dioxide. So then a question comes up, well, are clouds sensitive to changes in Earth's temperature? If the Earth is warming up, we certainly want to know how the clouds are changing. And so this is where we can talk about cloud feedbacks on climate. So there's been an increase in carbon dioxide, which has caused the Earth to warm up by a certain amount. So we could ask, well, with a warmer Earth, maybe the cloud properties will change slightly or more substantially. And so, like, how will the cloud greenhouse effect change due to the warming of the planet? Well, if the cloud greenhouse effect becomes stronger, that's going to exacerbate the warming that came originally from the carbon dioxide. So the clouds will add to this effect. They'll make it worse. On the other hand, if the cloud greenhouse effect gets weaker as a response to the warming of the planet, that will mitigate the warming produced by the increase in carbon dioxide. You could also ask the question, how will solar reflection by clouds change? Well, when the planet warms, if the clouds reflect more solar radiation than before, that will mitigate the warming. On the other hand, if they reflect less solar radiation than before, that will act to exacerbate the warming produced by anthropogenic increase in carbon dioxide. So this exacerbation of warming would be a positive cloud feedback, where the change in clouds in response to the increase in temperature adds to the warming. Here it would be a negative, where the change in clouds in response to the warming of the planet act to reduce the warming. And getting more specifically, here are some of the effects that could act to produce a positive cloud feedback. For example, we'd have a positive cloud feedback if there are more high-level clouds in a warmer world than there are in a colder world. If there are fewer low-level clouds, so there's less solar reflection. There's an increase in the height of cloud tops, so they emit less radiation to space than before. That will act to exacerbate warming. Or if there's a decrease in the thickness of clouds such that they reflect less solar radiation, that will exacerbate the warming. And we can get the reverse negative cloud feedbacks if the opposite happens. Like, for example, if there are fewer high-level clouds, there will be less restriction of outgoing long-wave radiation to space emitted by the surface. So the surface will be able to cool more effectively, and so forth. Okay, so now we can have a lot of different individual cloud feedbacks with respect to what types of clouds change and how their properties change. So we could ask the important question is, well, in aggregate, if we add up all of these effects over the whole planet, is the cloud feedback positive or negative? This is a very important question, because if it's positive, that means the warming from increased carbon dioxide will be worse, and then it'll make it worse. But if it's negative, then the warming we expect from carbon dioxide will be mitigated. Well, what's the answer to this question? We don't know. We don't know. And clouds have been and continue to be the greatest source of physical uncertainty in our understanding of climate change. You may have heard about the upcoming IPCC report, which was summarizing our current knowledge of climate change. And I was reading in the summary, which has already come out, that yet again, they state in the summary, just like they did in the previous reports from 6 years ago and 12 years ago, that the biggest physical uncertainty is still the role of clouds. Okay, so how can we try to estimate cloud feedbacks? One way we can do it is with a global climate model that simulates as much as we can about the climate system. And so we could put in some, double the carbon dioxide that's going to increase the warming of the planet, and we could see how the clouds change in this model, and then figure out the cloud feedback from that. The other option, which I'll talk about later, is we could look at, the planet has warmed up in the last several decades. We could see how clouds changed as the planet has warmed up in the past several decades. Well, let's first look at the models. What this is, these are models that went into the upcoming IPCC report. And they just are given letters here as signifiers. So I don't know which models these are in particular, but I just want to compare all of them. And this is the change in the radiation due to clouds as in ratio to the change in radiation due to carbon dioxide. So if it's negative, that means the clouds have changed so as to keep more radiation in the planet. If it's positive, they've changed to increase the the radiation leaving the planet. And you can see there's quite a discrepancy about which models say what will happen. Will the clouds increase the radiation leaving the planet, or will they reduce it? Well, it's all over the map here, positive and negative. And in fact, they can't even agree on what's doing it. Like, for example, these two models here say it's going to be about the same amount on net, but this model here says it's going to come through the long wave or the thermal radiation change with no change in reflected shortwave. This model next to it says no, the thermal part won't change very much, but the reflection of solar radiation or the shortwave radiation is what's going to do it. Or here's a model which says there's not really going to be any change in radiation flux due to clouds. You know, like this one, very little effect. This one next to it says, well, there's not going to be any net change in radiation due to clouds. That's because the thermal effect is going to be really canceled out by the solar reflection effect. So they're all over the map, very inconsistent between the models. And this has been something that has just been persisting for a couple of decades. It's been a long-standing problem. Well, why is it so difficult? Well, global climate models, what they do is they want to solve the equations, say, relating wind and radiation, temperature, moisture, and step forward in time to see how the atmospheric circulation, ocean circulation, different things vary. The clouds, other effects be related to land surface chemistry, the ecosystem. And you have to break down the planet into chunks and solve these equations for each chunk, and then they could exchange information or radiation, mass, heat, moisture with the adjacent chunks. Like winds can come in and out from the adjacent grid boxes. Okay, the difficulty is with the current computer resources, these chunks have to be very, very large, say 250 kilometers wide and 1 kilometer high. So that's a very, very large area, and all the equations are doing is just telling you what the average properties in this area are changing. Well, clouds are very much smaller than this, and cloud processes are circulations very much smaller than this. These are things that we don't have the computing power to actually simulate. All these processes important for cloud formation happen at much smaller scales. We can't directly simulate it, and so we have to approximate it by what we can simulate, which is the grid box mean property. So we don't know what the average temperature is at 250 kilometers, the average wind, and we have to figure out what all these little clouds in here are going to do. That's very difficult. And so the lack of computing power requires that we use approximations in cloud processes, but the sensitivity of Earth's climate to small changes in cloudiness means we need to have great precision in the simulation of cloud processes. Since just a few % change in cloudiness can equal the amount of radiative change we've had from CO2 since pre-industrial times, we really have to get down to be as precise to correctly simulate cloud changes, you know, within a few %. But you can't do that with approximations. These are incompatible. And so what happens is all these different models, they have different cloud processes, different ways of approximating the cloud processes. We don't know which one is right, if any of them are right. There's just different ideas of how to do it. And they all have different cloud responses to global warming. And so what happens is if you put in a climate model and say, well, carbon dioxide is going to increase at some rate going into the future from the year 2000 to the year 2100. How much will the planet warm up? And of course, there's going to be warming from the increase in carbon dioxide and other greenhouse gases. There's going to be warming from melting of polar ice that allows more solar radiation to be absorbed by the dark surface. And there's also going to be responses in how the clouds are. And you can see each one of these is an individual model or an average of many realizations of an individual model that predicts how temperature will change. There's one up here saying it's really going to go up very high, 4.5 degrees Celsius in the global mean. There are other ones down here that say it's only going to go up 2 degrees. maybe the average, which is this dark line, says around 3 degrees or 2.5 probably from 2000, but there's a very large spread. Now, there are many things that contribute to this spread, but the largest factor is the different ways clouds are handled. And so the reason why it's so uncertain, the future trajectory of warming here, is how do you do the clouds? And until we figure out how to do the clouds better, I don't really foresee making this range of possibilities shrink down. Well, since we're having a difficulty with the models, the climate models, maybe we can look at observed cloud trends, because it's been a case that global mean temperature has increased over the past several decades, so the Earth has gotten warmer. How have clouds changed during the same time period? Of course, we have two caveats here. One is temperature is not the only thing that affects clouds or can potentially affect clouds. There's other processes, just like changes in atmospheric circulation. So just because we see a cloud change over the past several decades doesn't mean it's due to global warming. And also, one larger caveat is that the observing systems in the past and currently were not designed to monitor changes in climate. They were designed to monitor daily weather. And so we've sort of, after the fact, tried to put together something that could look for changes in long-term things that are related to climate, but these observing systems were never intended to do that. Okay, so one cloud observing system, which I've used in my research, it's called the Extended Edited Cloud Report Archive. You don't need to worry about that. I just want to put up there to give it credit. These are visual cloud reports made by observers at weather stations around the world and also aboard ships, primarily just freight ships or container ships that just travel across, carrying things from China to the US and other places. These are visual cloud reports, so just a person goes out, looks into the sky, and says how much the sky is covered by clouds, what types of clouds are they, something like that. That means there's no quantitative information on cloud radiative properties. And also, there's a lot of undersampling because it's just a point observation, and especially over the ocean, you only have an observation where the ship travels, and over much of the ocean, there's hardly any ships traveling there, with any frequency. Of course, the advantage of this, despite these disadvantages, is it goes pretty far back in time, where we can get global data over the ocean back to 1952, and currently 1971 over land. Now, for individual nations, you can get cloud observations going back even earlier than that. Another cloud observing system is the International Satellite Cloud Climatology Project. And this is just cloud measurements made by a disparate collection of weather satellites put together into a cloud record. So it does provide quantitative information on cloud radiative properties, and it gives 3 hourly sampling over the entire globe. So we have very good sampling, but the disadvantage is, these data only go back to 1983, because you only have them where you have the weather satellites capable of doing this, and those don't go back very far in time. So here I've done a comparison of these cloud variations over land. On the left here is low latitude land areas, so equatorward of 30 degrees latitude, and on the right here are northern hemisphere mid-latitude land areas between 30 and 60 degrees north. And the satellite cloud time series, how the cloud record is in blue, and the surface visual observations are in red. So you see this top line shows changes in upper level clouds, clouds higher in the atmosphere. There's actually a lot of agreement during the period of overlap between the surface record and the satellite record. That's also true over northern hemisphere land. Actually, this is like the best place for surface observations because it includes Europe, United States, places like that where there's a big density of weather stations. There's substantial disagreement between the surface and the satellite record for total cloud cover, all clouds. Now this agreement comes because there's a disagreement between low clouds. The upper level clouds, there's agreement, but because upper plus low is total, this disagreement in what the low level cloud is doing shows up in total. And so over the land stations, the surface observer says there's not much change in low level cloud. The satellite says there's a big decrease in low level cloud amount. And this bottom one is cumulus, but I won't get into that now. Now, here's the same comparison over ocean, looking at low latitude tropical ocean and also the North Pacific, North Atlantic on this side. So again, agreement for upper level clouds during the period of overlap, here and here, a lot of agreement. But then disagreement for the low level clouds. The satellite record says low level clouds are decreasing. The surface record over the ocean says they're increasing. It's a big disagreement. This one spike here in the satellite record is not a real cloud change. It comes from the interference from volcanic aerosol from the Mount Pinatubo eruption in the early 1990s. Okay, so just a summary of the results. The satellites and the surface observers generally agree about upper level cloud variations, at least during the period of overlap. That gives us a little bit of confidence that maybe we're getting the right true record. They really disagree about the low level and total cloud variations that have occurred over the past couple of decades. So at least one of these cloud data sets has to have spurious low level cloud changes, something that's not real. So let's take a look at the satellite data set. We'll look at total cloud from the satellite. This is the global mean time series. So in the mid-80s, there is an increase or a reported increase in total cloud amount by the satellites, and a decrease to the year 2000 and an increase again. What I've done here is I've taken this change in the global mean and calculated the correlation from the change at each grid box with that global mean. And so the places here that are red are the parts of the world that are really contributing to this global mean cloud change. And it has a kind of an interesting pattern. It's not really, doesn't seem to be really related to sort of geographical features. And then like there's this big spot here like an Indian Ocean where there's like rather drastic changes in how correlated the clouds here are with the global mean. Now what I've overplotted here this is the view area of some of the satellites that have gone in to the satellite record. This is like the European geostationary satellite that provides the weather observations for Europe. We also have this for the US, and so when you watch the news and you get the weather report and it shows the cloud fields going across the country, probably it's coming from this satellite that's in this position. There's also one for the Japanese. And so here you see these features, are really associated with the satellite geometry. So this indicates to me that most of the features contributing to the global mean time series, they're related to satellite geometry. It doesn't look real at all. And I don't really blame this data set because this is a very hard thing to deal with. I mean, these sensors in the satellites, they degrade, the orbits shift. The cloud record is constructed from many different satellites with differing sensors. The calibration procedures, they tried to do it, as a heroic effort, but simply insufficient for climate monitoring, but it's fine for weather, and that's what the satellites were designed for. They were designed for weather. And so I conclude that the current errors in the long-term satellite cloud record are just greater than the precision we need for climate monitoring. Well, let's go to the surface observations. Let's look at the low-level cloud change. You may that there is a big increase in low-level cloud reported by surface observers on these ships. Is that real? I mean, these are pretty big changes, up to 9% sky cover. Some of these I know, like in the North Pacific, appears real because it's related to changes in atmospheric circulation, but there's widespread areas over the tropical ocean where there's big increases in low-level cloud cover that have been reported. Well, I'm kind of suspicious of that because over the tropical oceans, it doesn't seem consistent with the meteorological changes that I've examined. I won't show that here. And also, if there's been a really large increase in low-level cloud cover, well, that would act to reflect more solar radiation back to space without having much influence on the cloud greenhouse effect. So that'd be a cooling effect, a strong cooling effect, but we haven't seen that. The Earth has been getting warmer, so it looks like this is, too large an effect from too large a change in low-level cloud cover to be real. Part of the problem may be related to the way surface observers report clouds. On the right here, I've shown stratocumulus, which is mainly overcast clouds with a couple of breaks there. Here, I've shown cumulus clouds, and the surface observer reports how much of the sky dome is covered by clouds. And so you notice that from the surface observer, both here, this appears completely cloud-filled from the perspective of the surface observer, and also here, it appears completely cloud-filled. But if you look down, at the horizontal plane, there's these big gaps here that the surface observer doesn't see. So that's why cumulus is very difficult to accurately get from surface visual observations. And so perhaps the trade cumulus, which are very prevalent over the tropical ocean, are getting taller but not wider, so they would appear to have more sky cover to the surface ship observers, but not really have more sky cover in terms of affecting the radiation budget of the planet. Of course, the surface ocean data have problems. There's not few observations over much of the ocean. The ship observers receive little training. They're not like at weather stations. Different nations may have slightly different observing procedures, so that if one nation, their ships start going to a different part of the world, they can sort of contaminate what clouds are reported compared to what it was there before. Or if they have a larger proportion of world shipping, they could produce an apparent bias in the clouds because they report it slightly differently. It's difficult, as I said earlier, to convert cumulus sky dome cover to horizontal cloud cover. And again, we don't have quantitative information on possible changes in cloud thickness, because, like, for example, if the cloud cover, low-level cloud cover has increased, but the clouds have gotten thinner, maybe there's no net effect on solar reflection. Just one final point. I'd like to come back to the upper-level cloud cover that seemed to be more realistic in comparing the two data sets. What I've shown here is just the mean climatology of upper-level cloud cover as seen by surface observers on these ships. And if you recall from the earlier plot I showed, there's a lot of convective activity, rain, cumulonimbus, over Indonesia, which is you see a lot of upper-level cloud cover, and also along the intertropical convergence zone here. And then in these regions in the subtropics, there's very little upper-level cloud cover. It's in the subsiding part of the Hadley circulation, so it's really dry in the atmosphere above the boundary layer. So there are very few upper-level clouds there. Now, the arrows at the surface show the surface winds. And you can see how the surface winds, the trade winds from the southern hemisphere, from the northern hemisphere, are converging here. The convergence is in these dashed contours. They're surface convergence, so from continuity, if you have convergence at the surface, you're going to have upward motion. So that's what's generating a lot of rain and putting clouds high in the atmosphere. And also we have a lot of convergence over the Indonesian region too. What I plotted here on the bottom is the change in upper-level cloud cover at each one of these grid boxes. This is just the change. And so here you see there's been an increase in the cloud cover in this location, and there's also been an increase in convergence. So that's consistent. We have more surface convergence, more upward motion. That's going to generate rain and deep clouds that extend high in the atmosphere. In these other places, they have divergence, so they've dried out a bit, so some of the upper-level cloud has gone away. And I should say that this is just going to be a smaller change compared to this climatology, so it's not like all of these clouds have shifted over there. It's more like just like there's been a shift of some of these clouds more to this region here. So there's been a shift, somewhat of a shift in the cloud convergence to there. And this rather resembles the pattern associated with El Nino, where when you have El Nino, the ocean warms near the equator in the central Pacific, and it shifts the precipitation out to that direction, and you get more clouds there. So it's rather El Nino-like. Well, so it looks like upper level cloudiness is decreased over most of the tropical Indo-Pacific Ocean. Not over every area, but most of them have blue. So on average, it's decreased. Tropical circulation has become more El Nino-like, but we can't make a direct attribution to global warming because this could just be a change in atmospheric circulation that happens from natural variability. Maybe it's associated with global warming, but we can't be sure. So let me now summarize. So just clouds, they reflect solar radiation back to space. They reduce emission of thermal radiation to space. And different cloud types have different radiative effects. Small changes in clouds can have big impacts on Earth's radiation budget. And through affecting the radiation budget, they affect the climate by changing the temperature of the Earth. Global climate models have to approximate cloud processes, and I think this will be, for the foreseeable future, we're not going to have enough computing power to be able to get down at the small enough scales to actually directly simulate these clouds without approximations, I think, for a couple of decades. And of course, when we do use approximations, it introduces large uncertainties into the simulation of clouds, and these uncertainties introduce large uncertainties into predictions of future global warming. And this is one of the reasons why when there's a range given to how much they think the world may warm up by 2100, this is one of the primary reasons why there's that large range in uncertainty. Okay. Cloud records obtained from satellites and surface observers, they exhibit some long-term variations that appear spurious. Sometimes I know why that is, like with cloud geometry. On the other hand, there are some things I don't understand why it appears spurious. I mean, satellite geometry. The uncertainties in the cloud observations are greater than the precision needed to assess the impacts of cloud changes in the past several decades on Earth's radiation budget. So we can't actually say, have clouds changed or not? The uncertainties are too great to know if they've actually changed or not during the past several decades. Although some regional cloud changes are consistent with changes in atmospheric circulation, so I think those are real because there are multiple data sets that agree on that, and that provides more confidence that it's a real change. Satellite and surface observations suggest that upper level cloud cover has recently decreased over much of the globe. I just talked about the Indo-Pacific region, but it's also decreased over tropical land areas. It appears perhaps associated with decreases in precipitation over tropical land areas. All else the same, this decrease in upper level cloud would allow more thermal radiation to get to space. That would be a cooling effect, but we can't really conclude that there's been a net cooling effect until we know what changes have occurred in solar reflection by clouds, since the net cooling is going to come from the combination of the solar reflection effect and the cloud greenhouse effect. Just like one recommendation I would make based on this is that we really need a dedicated and a stable observing system to systematically monitor changes in clouds and radiation over several decades. These are small changes in clouds we need to figure out because they could have big changes on a radiation budget, and it's difficult to do that just from systems designed for purposes of weather. And we need to make sure that we have stable observations and over a lengthy period of time. Anyway, thank you. Okay, a question about effective aircraft contrails on the thermal part and the solar reflection part. It looks that certainly the contrails are probably going to have a net warming effect because they're pretty thin. You can see the sun through them. That means the solar radiation gets through them, but they do restrict how much thermal radiation is going out to space. But I think overall it'll probably be a pretty minor player because it needs kind of special conditions for contrails to form and to persist. And usually when that's happening, there are some other cirrus clouds already there. And it certainly have large regional effects like over Europe and over the US where there's a lot of aircraft, but probably not a very substantial global effect. Okay, back there.
Scripts designed to build the satellite, designed to try to help answer this question. Where do we stand with that?
Oh, okay, yes. That's sort of a sore point because basically Scripps, some investigators at Scripps, they built a satellite for NASA that would monitor the entire hemisphere of the Earth at once, something that no other satellite has done so far. They're too close, but there's going to be far enough out that it can see the entire hemisphere at once, so it'd be very good at monitoring changes in cloud and radiation. The satellite has been built and it's sitting in a warehouse for several years because NASA does not have the money to launch it, and as far as I know, they're not planning on ever launching this satellite that's already cost several $100 million to build. You know, the NASA budget, I mean, this has been a concern with the NASA budget, has really been with the goal to go on to the moon and to Mars, but not to increase the budget for that. A lot of the Earth science capabilities have been cut out. So it looks like after this current set of satellites goes up by NASA, there's not going to be anything that will replace them. And in fact, one of the basic measurements is like with the Earth radiation budget, and also like how much radiation, solar radiation, does the sun put out. You know, that changes a bit over time. It looks like there's going to be a break in the record. They're not going to be, after when we get into the next decade, there's going to be a period of time where there'll be nothing that will measure the solar output. Yeah, you mean the anthropogenic part, or just, okay. Yeah, I mean, the polar regions are rather difficult because they're pretty bright and they're pretty cold, and so, you know, the effects of clouds by being bright and cold is really often difficult to distinguish them. And oftentimes you could get like this thin ice crystals, like a cloud at the surface that's very thin. It looks like there's been more haze in the Arctic just from anthropogenic pollution that may have been having a warming effect. A lot of times this haze has a cooling effect, like with a lot of the pollution. You see it's very hazy, the sky is white. It's reflecting solar radiation away like over the continental US. But in the Arctic, because the surface is so bright, it could actually have a warming effect and emit thermal radiation back to the surface that may have been having some effect on the warming in the Arctic, although I don't know quantitatively how important that's been. Okay, so let me address the volcanic eruption first. Mount St. Helens actually didn't have a very big global impact because it kind of blew off to the side. It didn't blow straight up, but off to the side. And so a lot of the material didn't get into very high up in the atmosphere, and so it didn't last very long. But on the other hand, you saw the effects of Mount Pinatubo, which has been the biggest recent eruption, where it lofted a lot of sulfur into the stratosphere and produced like these little haze particles that cooled the planet for several years. They interrupted like the upward trend for global warming, but of course after several years those particles washed out, and so the globe continued to warm after that. It's not clear that it's had any real change on the clouds. It appears in the satellite record because it interferes with the cloud retrieval, but that's probably just an artifact in the cloud retrieval rather than a physical effect on the clouds. I mean, like although it's a very big area of research to figure out what these pollution particles, how they affect clouds, just not from volcanic eruptions, but just from fossil fuel burning. And the other question with 9/11 is they downed no aircraft flew across the U.S. for a couple of days. So it was a very interesting climate experiment because there were no contrails and no output from that, and it looks like, I haven't read the specific studies, but I think they found that there's a little bit more there was a change in temperature, but I don't recall what it was. So I'm sorry, I can't really specifically answer that one. I'm trying to remember. You know, if it was higher. Yeah, because like I guess it just was. I think it was higher, although.
I heard it was clearer and colder. Yeah, the nights were clearer and colder.
Okay. Okay. So that would be consistent with there being less contrails that would be emitting thermal radiation back down to the Earth. And so that, you know, you'd have more radiation being able to escape then. So that would be because it's clear and make it colder. That's a good question. How would a satellite dedicated for long-term cloud climate monitoring differ from a weather satellite? Well, one difference is for long-term climate monitoring, you want a very stable measurement. You don't want the sensor to degrade, or at least you want to know how it degrades, so you don't get like some artificial trend just because the sensor can't detect clouds as well, so you think there's less clouds there. For a weather satellite, that's not really important. Another thing that could change is the satellite could drift, and so like usually it passes over a place on Earth like at 1 p.m., but now it passes at 3. Maybe at 3 there's fewer clouds then, but that's just because you're looking at a different time of day, so it appears like there's a cloud change, but just because the satellite's looking at a different time of day because of the orbital drift. For weather, though, that doesn't matter really, because you still see the hurricane, you know, the hurricanes, you know, something like that. Also, with a weather satellite, if you can put up a new satellite that has some, you know, advanced instruments, you can get some better measurements that would help you, you know, forecast hurricanes or other weather events better. That'd be something important to do. Whereas with climate monitoring, you would like to keep using the same measurement technique over and over again. You know, like if you switch to a different thermometer for measuring temperature, maybe you could do a better temperature measurement, but it'll break that nice long continuous record.
Ladies and gentlemen, Dr. Joel Norris. Appreciate it.
Thank you.
Okay, that will conclude our lecture for tonight. I want to thank you again for all of your support, and we look forward to seeing you next time. Thank you very much.